thinking back to the early 2000s, companies like Google, they were facing this almost impossible challenge, weren't they?
They really were.
How do you index an internet that's just exploding? I mean, petabytes of data every single day. Their old tools, the traditional databases, they just couldn't cope.
No, they were buckling under the strain. It was a genuine data deluge, a crisis of scale, you could say.
Yeah.
And, well, that's exactly the moment MapReduce really stepped onto the stage. It fundamentally changed how people thought about processing huge amounts of data, especially within that whole Hadoop ecosystem.
Right.
It wasn't just, another piece of software. It was a totally different way of thinking about building systems that were reliable, scalable for truly massive data sets.
So it enabled businesses to handle like unprecedented amounts of information.
Exactly. Quickly, reliably, and at scale. It started powering all sorts of things, analyzing user behavior, crunching through server logs, even, laying some of the groundwork for the AI models we see today.
Okay, let's really dig into this then, because anyone who's even like dabbled in big data knows the name MapReduce. It's foundational. But sometimes the genius is in its simplicity, right? So what is MapReduce really at its heart? And why does it still, matter so much now in 2025? Let's take a look at the sources you brought and try to distill that.
Okay. Well, fundamentally, MapReduce is a programming model. You could almost call it an architectural pattern, really. It sits within that Hadoop world.
Right.
And it's specifically designed to chew through those colossal data sets we were just talking about. It kind of democratized big data processing in a way.
How does it do that, though? It's famous for those two main parts, isn't it? Map and reduce. How do they simplify things when you're dealing with, like, internet scale data?
That's a great question. So the first stage is map. The core idea here is you take this massive data set, you split it up into smaller, much more manageable chunks. And then you process each of those little chunks in parallel, spread across potentially many, many machines. Think of it like a huge team sorting mail. Everyone gets a small pile.
Gotcha. Parallel processing.
Exactly. Then comes the second stage, reduce. This is where you take all those intermediate results that came out of the map stage.
From all the different machines.
Right, from all the different mappers. And you aggregate them, you compile them, basically, into your final meaningful output. What MapReduce really nailed was handling the complexity, managing state, dealing with failures when you've got tons of machines working together. Before MapReduce, building that kind of distributed system was incredibly complex, very custom for each job.
Right, bespoke every time.
Yeah, MapReduce gave you this elegant abstraction that took care of the really hard parts automatically.
And this is where it gets really clever, isn't it? The whole distributed computing aspect. Tasks aren't just queuing up on one machine.
Yeah.
They're running at the same time across maybe hundreds, even thousands of machines, nodes in a cluster. That saves a massive amount of time and resources.
What was the specific problem that made Google need this distributed approach so badly?
Well, it was scale, fundamentally, and resilience. They were literally trying to index the entire web.
Wow.
That task is just too big for any single computer. MapReduce let them shatter that huge job into millions of tiny independent pieces that could all run at once.
Okay.
And it wasn't just about speed. The practical benefits are huge. It's fascinating how it tackles problems that would just, swamp older systems.
Like what specifically?
Well, first off, efficiency for big data. I mean, it can process petabytes of data across these distributed clusters. That kind of scale was almost unimaginable before.
Petabytes. Okay. That's a jump from terabytes even.
Oh, yeah. Then there's scalability. This is key. Need more power.
Just add more machines.
Pretty much. You just add more nodes to the cluster. You increase your processing capacity without having to re-architect everything from the ground up. And you mentioned resilience earlier, because with that many machines, surely things go wrong sometimes. Computers fail.
All the time. And that's crucial. MapReduce is built to be incredibly fault-tolerant. If a node fails mid-job, MapReduce automatically handles it. It basically reruns the failed task on another healthy machine without losing data. I remember hearing stories, maybe exaggerated, maybe not, about early clusters losing like half their machines during a big computation.
And the job just kept going.
And the job just finished. That kind of resilience was, well, revolutionary back then.
Wow.
And maybe one of the biggest wins, especially in the early days, was cost effectiveness. It was designed to run on commodity hardware.
Meaning just standard off-the-shelf computers, not expensive supercomputers.
Exactly. You didn't need specialized high-end machines. That massively lowered the cost barrier for organizations wanting to process huge data sets.
So just to connect that back for you, the listener.
Yeah.
When we talk about handling petabytes on standard hardware with fault tolerance built in, what does that really mean?
Yeah, what's the takeaway?
It means businesses, researchers, they could suddenly tackle these enormous information challenges without needing a massive budget or worrying constantly about data loss if a server died. It really did, like you said, democratize large-scale data processing. Okay, so we get the power, the importance, but how does it actually work? Under the hood, how does this distributed magic happen? Maybe walk us through the steps simply.
Sure. It's quite an elegant flow, usually in 4 main steps. First up is input splitting. Your massive dataset gets broken down into those manageable chunks, the splits, ready for parallel work.
Okay, step 1, break it down.
Step 2, mapping. Each of those splits gets fed to a mapper function. This function runs in parallel on different machines and processes its little piece of data, spitting out what we call key value pairs. These are like intermediate answers.
Key value pairs, got it.
Then step 3, shuffling and sorting. Now, this sounds simple, maybe just moving data around, but it's actually where MapReduce does some really clever stuff to handle network traffic and data locality efficiently.
Ah, so it's not just random shuffling.
No, definitely not. All those key value pairs from the mappers get grouped together based on their key. So all pairs with the same key end up together, and then they're sorted. This gets them ready for the final stage.
Yeah.
Getting this shuffling step right is often critical for performance, actually.
Makes sense. It gathers related stuff together.
Precisely. And finally, step 4, reducing. The reducer function takes each group of sorted key value pairs, grouped by key, remember, and processes them to produce the final output. It combines or reduces those intermediate values into the result you wanted.
Okay, let's make that concrete. You mentioned an example from the sources, counting words.
Yeah, the classic example. Imagine you have a massive book, like terabytes of text, and you want to count how many times each word appears.
Okay.
MapReduce first splits the book into chunks, input splitting. Then, different mappers on different machines each read their chunk and output pairs, like word 1, for every word they see. Mapping.
So like Thor 1, Quick 1, Brown 1, Fox 1, Thal, lots of those.
Exactly. Then the shuffle and sort groups all the pairs for the same word together.
Wow.
So you'd get the 1, 1, 1, Quick 1, 1, Brown 1, and so on, all nicely sorted.
Ah, I see. All the ones for each word collected.
Right. Finally, the reducer takes each group, like the 1, 1, 1, sums up all those ones and outputs the final count, the 500, Quick 20, etc., reducing.
That makes it super clear. It breaks down a huge counting job into parallel counts and then a final summation.
Yeah.
Very neat. So now let's look at where this approach actually gets used. Where does MapReduce pop up in the real world today?
Oh, it's still in a surprising number of places doing heavy lifting. A big one is log analysis, processing huge volumes of server logs to find errors, security issues, understand performance.
Makes sense. Logs are massive and unstructured often.
Exactly. Then there's e-commerce analytics, analyzing, what customers buy, click patterns, purchase histories, trying to understand behavior from vast amounts of data.
Right. Personalization and recommendations often rely on that kind of back-end processing.
Definitely. Scientific research is another area. Think about processing satellite imagery, analyzing huge genomic data sets, crunching numbers from physics experiments. MapReduce is great for those big batch jobs. And also financial risk analysis. Banks and financial institutions use it to sift through massive transaction data sets, looking for patterns of fraud, assessing risk, that sort of thing.
It's amazing, really. So much of the digital world we interact with, from shopping sites to maybe even our bank's fraud alerts, has processes like this humming away in the background.
Pretty much.
As you can hear, its applications really do cut across so many different fields, tackling everything from fraud detection to, while understanding the cosmos. It's incredibly versatile.
Absolutely. And if you zoom out, look at the bigger picture. MapReduce is still fundamentally a cornerstone of big data processing, especially when you're dealing with very large, perhaps unstructured data sets where you need reliable batch processing.
Even with newer technologies around.
Yeah, I mean, obviously things have evolved. You have tools like Apache Spark now, which are often faster, especially for iterative algorithms or more real-time stuff because they can do more processing in memory.
Right. Spark gets a lot of attention.
It does, and for good reason.
Yeah.
But MapReduce's simplicity, its sheer robustness and fault tolerance, and its efficiency for those really large-scale batch jobs, particularly on less expensive hardware, that still makes it very relevant. Many industries rely on it precisely because it's so dependable and cost-effective for certain kinds of massive tasks where data integrity is paramount.
That's a really important perspective. It's not always about the newest, fastest thing, but the right tool for the job.
Yeah.
So this brings up a really interesting question for you, our listener, to think about. Given how MapReduce first revolutionized our ability to handle information overload, and knowing that data is just going to keep growing exponentially, how do you think this ongoing evolution in processing power and techniques will change things? Not just in these industries we talked about, but maybe in your own daily life, your work, how we interact with the world in the years ahead.
That's a big question.
It is something to mull over. Thank you so much for joining us on this deep dive into MapReduce. We hope you found it insightful, and we definitely encourage you to keep exploring this fascinating world of big data.